Unless you've been living off-grid for the past few years, you've probably noticed something remarkable. Artificial intelligence is no longer a futuristic dream. It's here, shaping the world around us. It's in your phone, in your workplace, and increasingly, in the very fabric of society itself. For many, tools like ChatGPT have even started to replace Google as the go-to source for answers. Governments, tech companies, and universities are all racing to harness its power. So, it was really only a matter of time before someone asked the question, could AI be used to do science? Well, it turns out it already has been. While the public might think of AI as something new, scientists have quietly been using forms of it for decades, though not always under that name. But with the explosion of large language models and machine learning, AI is spreading through every corner of research, from biology and chemistry to, more recently, physics and astronomy. Now, that might either excite you or terrify you. Because if AI can write essays, paint portraits, and even compose music, could it also become a good scientist? Could it uncover the secrets of the universe? The surprising answer is yes, it can. With the right training, guidance, and purpose, AI isn't just helpful. In some cases, it's becoming an essential scientific tool, capable of solving problems no human could ever tackle alone. AI may one day change how we understand the universe forever, provided, of course, we don't hand over too much control. Today, we're diving into the incredible, and sometimes unsettling, ways AI is transforming the fields of physics and astronomy. From mapping dark matter to designing the next generation of scientific instruments, we'll explore how AI might just be the key to unlocking mysteries we've never been able to reach before, as long as we don't lose sight of what makes science, well, human. Let's start with a story. In September of 2023, a scientist named Bruno Altieri, who was working on data from the newly launched Euclid telescope, noticed something strange, something fuzzy, in one of the telescope's early images. Now, Euclid had just begun its mission, surveying over a third of the visible sky to study dark matter and dark energy. And what Altieri found in the data turned out to be nothing short of extraordinary. He had discovered an Einstein ring, one of the universe's rarest and most fascinating optical illusions. At first glance, it looks like a glowing circle of light in space, but it isn't a physical object. Instead, it's the result of a phenomenon called strong gravitational lensing, where the light from a distant galaxy, hidden behind another, is bent perfectly around it by gravity, forming a complete ring. It's an incredible cosmic coincidence. The galaxies must be aligned with almost mathematical precision for it to happen. A tiny misalignment, even by a fraction, and you'd see nothing more than an arc, or nothing at all. But when it does happen, the results are stunning and scientifically invaluable. Einstein Rings allow scientists to calculate the total mass of the galaxy in front, including the invisible matter inside it. If the light bends more than expected, that's a sign of dark matter, the mysterious, unseen substance that makes up most of the universe's mass. Einstein Rings also magnify distant galaxies far beyond our observational limits, offering us a look at parts of the cosmos we'd otherwise never see. But here's the thing, while Altieri's discovery was lucky, it won't be luck that finds the next ones. Because Euclid is generating petabytes of data, hundreds of them. To put that in perspective, your home computer probably holds a few hundred gigabytes, maybe a few terabytes if it's powerful. A petabyte is 1,000 terabytes. Euclid's sky maps are so enormous that just 1% of the data released in late 2024 contained over 100 million light sources, stars, galaxies, and other objects. Hidden among those are potentially thousands of Einstein rings. But no team of humans could ever sift through that by hand. It would take centuries, and it doesn't stop there. Einstein rings, those strong lensing events, are just the beginning. Euclid's real mission is to study weak gravitational lensing, a subtler effect caused by entire clusters of galaxies bending light slightly, distorting the shapes of background galaxies. Now, that's not something you can simply see with your eyes. It requires detecting minute statistical deviations across billions of galaxies, patterns that only emerge in vast amounts of data. So how do you find something like that? That's where AI steps in. Machine learning algorithms can be trained on known examples of lensing, strong or weak, until they can recognize similar signatures in new data. It's already being done. Astronomers have used AI to identify 56 gravitational lens candidates in images captured by the Very Large Telescope in Chile. And in Japan, a citizen science project provided another breakthrough. Over 10,000 volunteers manually identified 20,000 galaxies in telescope data, which was then used to train an AI model. The AI went on to identify over 410,000 galaxies on its own, with 98% accuracy. This isn't just a time saver, it's a paradigm shift. With enough computing power, an AI can scan through Euclid's petabytes of data in weeks instead of decades, flagging hidden lenses, dark matter signatures, or even previously unknown galaxy types. It's like giving astronomers a second pair of eyes, ones that never blink, never tire, and see patterns humans could never perceive. Even if the AI isn't perfect, it will still uncover trends and relationships that deepen our understanding of the cosmos. Patterns that could lead to the next great discovery, maybe even about what dark matter truly is. But AI's role in astronomy doesn't end at pattern recognition. It's beginning to design experiments too. Take LIGO, the Laser Interferometer, Gravitational Wave Observatory. It's one of the most sensitive scientific instruments ever built, capable of detecting changes in distance smaller than 1/10,000th the width of a proton. Using two enormous 4-kilometer arms, it measures ripples in space-time caused by the collisions of black holes and neutron stars. Yet, even with that precision, scientists wanted more. One of LIGO's key engineers, Rana Adhikari, decided to see if AI could improve the observatory's sensitivity. So, he and his team developed a custom AI called Urania, gave it a list of allowed components, and told it to design a new system. At first, what Urania produced was nonsense. The designs looked like scribbles, messy, alien, and incomprehensible. But over time, as the inputs were refined, the AI's creations began to evolve. They still looked bizarre, asymmetrical, strange, but they worked. If implemented, Urania's designs would have improved LIGO's sensitivity by 10 to 15%. The only problem? No one on Adhikari's team understood why they worked. It took months of analysis before they realized the AI had rediscovered a long-forgotten theoretical concept from Russian physicists, a way to reduce quantum noise by recirculating light through a massive 3-kilometer optical ring. A principle no human had ever thought to use in LIGO before. That's the beauty and the mystery of AI in science. It doesn't think like us. It doesn't follow tradition. And sometimes that's exactly what science needs. Something that can explore outside the limits of human intuition. Today, more researchers than ever are turning to AI to push the boundaries of what's possible. In 2023, the journal Nature found that 8% of all research papers mentioned AI in their title or abstract, up from just 2% a decade ago. Over half of scientists surveyed said AI made their work faster, cheaper, and more accurate. Some even use AI to write and translate their papers, making complex research accessible to global audiences. Around a quarter of them said AI helped them brainstorm ideas, and 15% believed it could generate entirely new hypotheses. It's no exaggeration to say that AI is becoming a silent co-author of modern science. But, as with all revolutions, there's another side. Because while AI can be brilliant, it can also be blind. As we saw with the LIGO experiment, scientists didn't immediately understand how the AI reached its conclusions. And if you can't understand the reasoning behind a result, can you really call it science? The purpose of science isn't just to get answers, it's to understand why those answers are true. If an AI spits out a discovery we can't explain, then what have we really learned? This is one of the biggest challenges facing researchers today. In 2024, the Royal Society, the UK's National Academy of Science, issued a major warning. They urged scientists to be vigilant, to make sure AI-generated data isn't contaminated or even fabricated. Because yes, that can happen. AI can literally make things up if it thinks it's being helpful. They also noted that more and more machine learning studies couldn't be reproduced, a cornerstone of scientific validation. If no one, not even the original researchers, can recreate the AI's results, how do we know they're real? In that same Nature poll, 70% of scientists said they feared AI could spread misinformation or make plagiarism harder to detect. Over 60% worried it could introduce hidden errors or biases into data. After all, AI learns from us, and humans are full of bias. Bad data in, bad data out. Thankfully, astronomy is one of the safer testing grounds. If an AI claims there's a galaxy at certain coordinates, all you need to do is point a telescope and check. But when you're dealing with millions of detections, even simple verification becomes a monumental challenge. It's a trade-off. We gain speed, but we risk certainty. That's why, despite all its promise, I can't be left to run science alone. It's a tool, an extraordinary one, but it still needs a human mind at the helm. Because in the end, the heart of science isn't data, or computation, or even discovery. It's understanding. AI might help us see the patterns of the universe. It might even design the tools we'll use to study it. But for now, it's still up to us to decide what those patterns mean. The future of discovery will belong to those who can balance both worlds, the raw computational power of AI and the curiosity and skepticism that define humanity. I, for one, can't wait to see what we uncover when the two work together. Because as Euclid continues its survey, and as AI digs through the mountains of data it's producing, somewhere in that digital ocean lies the next great cosmic revelation, waiting for a machine to find it, and for a human to understand it. If you enjoyed this exploration of AI's role in science, don't forget to like, subscribe, and join me next time as we continue our journey through the cosmos, one discovery at a time.